Good morning. It's still morning. I am Mike Wamsley, Product Management with TE Connectivity in our Aerospace and Defense Group. A lot of years in connector development, and I'm pretty actively involved in VITA. So I'm going to talk about the next-gen VPX connector. So this is the connector at the plug-in module to backplane interface that Steve had alluded to. Show you the technology and what the advantages that it brings. I presented here at ETT in 2017. I showed this image because at the time we had a 3U VPX application, and everybody was pushing for more functionality, higher bandwidth, the things that Steve was just talking about. And at the time we had a 10 gig digital connector, 10 gigabit per second, our VITA 46 connector. Optical, you had one MT-and-a-half module. Coax, you had 4 coax ports in a half module. And I showed really what we were doing to develop and to increase both coax optical density and increase speed on the digital connector. So where we are today is we do have a 25 gig solution. VITA 46.30 supports 25 gig and really up to 32 for some applications for PCIe Gen 5. We also have higher density coax and optics. There was a lot of work done to develop higher density interfaces. So just to give you a couple examples, today we can get 10 coax and an MT in a half module, and we can get 3 full MTs within a half module. So there's been a lot of work there, but now it's 2025 and it's not enough, right? So the key objectives that came out of the study group, the 85.106 was a study group. A lot of industry leaders came together, some of the primes, COTS suppliers, backplane specialists, SI specialists. We had a really good collaboration of what's going to be needed for this next-gen connector. So double the pin count, support the higher data rates, increase current capacity. The mechanical fit, we wanted to stay within the 1-inch slot profile, make it modular, similar to what we have today, and make it compatible with all that coax and optics that we developed. We didn't want to redo all that. There's been a lot of work done. If we can re-leverage that into the existing next-gen VPX, that was one of the primary goals. And of course, support those rugged environments. So we're getting into doing all that environmental testing, the extreme vibration that Steve had talked about, et cetera, and making sure we're compatible with space right on the front end. So that turned into 56 different line items that we kind of went through and we did our development work on. So what came out of it was the VITA 100.30 connector. This is the revolutionary new multi-gig connector. So we're still using a wafer technology, similar to what we have today. You've got wafers that are specifically designed for higher speed signals. You've got power blades for power. They could be intermixed in different positions within a connector. And then we're achieving those goals. The significant pin count increase, addressing those higher speeds, the 100 gig lanes that we were talking about, and increasing our current capacity. So I'll talk a little bit about the features of the connector, not an in-depth discussion, but there's some key attributes that bring that technology forward. So in the plug-in module side, so the wafers now are strip-line 4-layer wafers, get better isolation, high performance material. So there's a little bit more advanced and a little bit thicker wafer than what we have in today's product. There are key slots in the wafers. As you get into higher density, the contact beams get narrower, the pads get narrower. It's more critical to get engagement and accurate alignment of those. So those key slots engage with the backplane and provide that alignment. You can see here, this is the 4 pair. There's actually 2 high-speed pairs for transmit to receive. There's a single end in between. So that keeps the TX and RX separation, also provides a single-ended line that can be used for other functions. And then on the backplane, we added ground shields in. You don't have that in today's VPX, but that provides isolation between the columns at the backplane interface. And then we maintained the 4 points of contact that are really requested for redundancy, space applications, high vibe, and then also no exposed pins to bend, same as today's product. So on the power blades, today's VPX has a FR4 based wafer with copper layer on it for power. Today, we're using a copper alloy. We're just stamping it. It's all metal alloy on the power blades. So we've got more than 2 times the current capacity over what we have today. So when we looked at this as a study group, we said, okay, here's the form factors, here's the voltage levels, here's the power levels that we want to achieve. When we looked at what the current the connector had to carry, 45 amps was where we really needed to meet to hit that 12 volt 6U application. So we've tested this, and preliminary test results show that we can hit 45 amps with margin on a single power blade. So we can use 1 power blade for input current, 1 for return current, and that keeps it dense, where you have 3 power blades today. It's a building block approach again. So here we have full modules, half modules. So in the VPX layout, you have P1, P2, you have P2B if you're using a half module. These connector modules are similar in width as existing VPX. So there we can take advantage of that and depopulate where we have coax and optics. Just take those pieces out. You'll note here we've got a 14 column and a 7 column for the full and half size. Today you have 16 and 8. The reason is we had to adjust the spacing of the wafers to a 2 millimeter pitch instead of 1.8. So we're losing a couple wafers per full column, but we're doubling the number of differential pairs per each wafer. One other addition that we're working through, some design proposals now, is slim guide hardware. So in the original VPX, when liquid cooling came about, there's a standard 48.4 that provides liquid cooling on 6U. We needed quick disconnects on the outer edges for the liquid cooling applications. To do that in today's VPX, we had to remove the guides on the outer side and just use 1 center guide. So here we're planning ahead, determined as a study group, we're going to support liquid cooling for 4U and 6U. We're going to put those guides back in on the outside. And to do that, we were going with slim guides that can fit. So we can still do a 6U that's shown on the bottom, put slim guides in the center and on the ends, and fit all 6 full connectors across that width. So a lot of this discussion with the technology leaders in the study groups really generated these ideas and led to this layout. We're even thinking about things like having features on the guides where you could attach mounting plug-in module covers to it. So really thinking through the application, what did we miss maybe as original VPX evolved, and what can we incorporate in the next generation? So one other application is higher pin count applications. So for high density switches, for example, they need a lot of I/O, a lot of pin count coming through there. So we've determined that we're going to release a 6-pair version. It's going to support a 1.2 inch pitch, not a 1 inch pitch. You can see from the view, it extends higher, taller off the carrier card, deeper onto the board, so it's not compatible with XMCs. But for applications like that, you typically would not rely on an XMC, and you'll get 50% more differential pairs coming through there. So I think Greg will talk a little bit about some of the apertures and the slot profiles. You'll see some 6-pair in there. What that does also is allows you more space for a taller aperture or a wider aperture. And we can effectively get 4 MTs instead of 3 MTs in that space. So I'm not going to run through these numbers, but just to highlight a couple things. So today you're at 64. If you take out the P0, you're at 64 high-speed differential pairs. We're getting to 112 with 4-pair and 168 with 6-pair. So significant jump in pin count. And then if you look at 6U, you've got 192 diff pairs. If you look at all those 6 connectors, you could go down to a 4U and get 168 with 4-pair or 252 with 6-pair. So you've got actually with 6-pair 4U slot profiles, you've got more differential pairs than you're getting in 6U today. So a big increase in pin count where that makes sense. So signal integrity was a big part of the development. We worked through this a lot, did a lot of presentations and modeling within the and shared results with the study group. But this is a big leapfrog in signal integrity. Some of the things I've talked about, the wafer, the shielding, et cetera, really gains advantage in reducing noise and performance at those higher data rates. So this is just a quick near-end crosstalk plot at like 28 gigahertz, which would be like a fundamental frequency for 100 gig lanes. You're at a 15 or 20 dB improvement over that at that frequency. So it's a significant gain over, and it's not just an extension of the existing VITA connectors. We also did a lot of work outside of the connector. So when you design a high-speed connector, you can't just design the connector. You got to look at route out and channels and look at it in application. So we really designed it for optimal PCB routing. We've got clean, straight routing lanes. We can get 8 mil traces through there, which is good for lower loss, longer reach on the backplane. No neck down or zigzagging required through those channels. And then we did channel models. So 85.106 study group said, okay, if we're going to build reference models where you run it through a channel from a plug-in card through the backplane into a receiving plug-in card, you're going to look at these trace lengths. We're going to use this board material. We're going to do this stack up. We ran a number of iterations and kept revising the design and shared those results, but we got very good margin with 100 gig lanes. And then finally, we did a routing study on a 12-slot chassis, just to show that, yes, it can be done. We did 182 diff pairs, routing over 10 layers from 2 switches out to payload cards. So we want to make sure from an application standpoint, the SI works and it's routable. One other interesting thing, we looked at this probably over 10 years ago, looking at putting AC coupling caps on the wafers themselves. So it's, being a wafer-based solution, you could put capacitors on the wafers within the connector. It was fairly complex back then. We really didn't have the volume to kick it off, but we're moving forward with it now. So with the VITA 100.30 connectors, we would have an option where the AC coupling capacitors would be installed within the connector. So it frees up the real estate. You don't have to put them behind the connector. It also improves signal integrity a bit as well. So, and then we're also looking at a couple other roadmap items. So we're looking at leveraging that technology for the next-gen power supplies. So Steve mentioned 100.40 being for power supplies. We're looking at, can we leverage that connector, since we're tooling it, to handle like the discrete signals. They need more pins than what's in VITA 62 today. Well, we got a high density solution with a lot of pin paths. And then the lower power contacts, what I call lower power, we could use those 45 amp contacts within a connector along that card edge for those. And then for high power, we have 100 amp contacts in our Multibeam Plus product line. So we're looking at altering those and putting them into a high power module to go alongside the VITA 100.30. So this provides a nice building block for power supplies. And then last roadmap item, this was discussed last year at Embedded Tech Trends by my colleague Mark Benton, but we have an optical transceiver that can go onto the wafers themselves. So we have this installed in production for IFE applications today. We're packaging it into the wafers themselves. So you've got 4 differential pairs coming off the board. You do the EO conversion, you've got 4 fibers coming out on each of those columns. So we're looking at how we can package that, building that blind mate interface, and that's in development today. So just leave you with the roadmap. The things I talked about on the left are in being tooled. We're kicking off tooling now. 4 pair connectors followed by 6 pair. The slim guides, connectors with caps on wafers. Those are all technologies that will be tooling, will be available by end of this year or next year. And then in development, right behind that is the next gen power. And then after that, optical transceiver.